Assalamu alaikum. This is the final curvature presentation for Future Gadgets Lab. Our project is rendering non-Euclidean geometry in a first-person perspective. Considering the fact that the current computer graphics framework is based entirely in Euclidean geometry, which is the normal geometry we observe in everyday life, rendering hyperbolic geometry requires thorough mathematical research and time to implement. With this project, we hope to create a framework already in hyperbolic geometry for people in the future. Examples of non-Euclidean geometry include spherical and hyperbolic geometry. This means that the geometry itself is defined by these shapes as opposed to Euclidean geometry, which is rectangular. This means that they cannot be defined in Euclidean space. These geometries must be defined separately with their own ways to measure distance. Let's consider an example. In the top right figure, the distance between point 0 and point 1 is the same as the distance between point 1 and point 2. According to Euclidean space, if we measure the arc length of the hyperbola, which in both cases would be 1 unit. Now, if we consider hyperbolic space, we already see a difference in the top left figure. The distances between point 0, and point 1, do not look the same from a Euclidean perspective. However, according to a hyperbolic perspective, they are exactly the same. This is because the metric of measuring distance in hyperbolic space is different than Euclidean space. Both of these distances, even though they look completely different right now, are actually 1 unit in hyperbolic space. You can see how this distance is measured in hyperbolic space in the second figure. Unlike Euclidean space, where the distance from the origin is x squared plus y squared plus z squared, the distance from the origin in hyperbolic space, which is called the Minkowski metric, is x squared plus y squared minus z squared. This matrix is then used to find the dot product between two vectors in figure 3, and that dot product is then used to find the distance between 2 points in figure 4 using the hyperbolic cosine function. This is the expansion of space that hyperbolic space presents us with. We can have much more information in hyperbolic space in a smaller region as opposed to Euclidean space because of this. However, our character would cover these distances in the same amount of time, even though the distance has increased in a Euclidean perspective, as you can see in the figure. This is because, again, these distances are 1 unit in hyperbolic space. To truly see the advantage of this expansion of space, we must consider a hyperboloid in 3 dimensions instead of a hyperbola in 2 dimensions. As you can see in the figure, this is a typical circle in Euclidean space with a radius of 2 units from the origin. This is a hyperbolic circle with a radius of 2 units from the origin in hyperbolic space. We can already see the difference between hyperbolic space and Euclidean space in that from a Euclidean perspective, this circle looks to have a radius of over 2. However, from a hyperbolic perspective, it is still 2 units from the origin. This shows us then how differently distances grow in Euclidean space and hyperbolic space. Euclidean space grows linearly while hyperbolic space grows exponentially. However, a character moving in hyperbolic space will still take the same amount of time moving these distances as they do in Euclidean space. This gives us the advantage of moving in the space quickly while also being able to add exponentially more information. We now move to a more practical example. The hyperboloid is the hyperbola in 3 dimensions. We can see its exponential nature in the top right figure, where as we move the red circle upwards on the hyperboloid, the radius will increase exponentially. Using the previously shown equation of arc length in hyperbolic space, we can mathematically prove this exponential nature. In Euclidean space, our origin is 0, 0, 0. However, if we consider the tip of the hyperboloid to be our origin, it becomes 0, 0, 1. Then, if we use our previously defined dot product to find the distance of an arbitrary point xyz from the origin 0, 0, 1, we get the following equation. We can observe this exponential nature by looking at r, which is the hyperbolic radius. R is the exponent in our equation. This causes the space to increase exponentially because the hyperbolic radius is increasing exponentially. This also means that if we want to move from one point on a hyperbolic circle to another point on a hyperbolic circle, it is possibly better to move to the origin and then to our endpoint instead of moving along the actual circle because of how the exponential nature of hyperboloids work.
This is what our level looks like. The outer squares lie along the circle of radius 2. We will start from one blue square and our goal will be to reach the other one. First, ignoring the obvious path, we will try moving along the outermost squares and see how long that takes. This is equivalent to moving along the edge of the circle. Now we will first move directly to the origin and then the blue square. That was way shorter. More importantly, did you notice that there are 5 squares around a corner and that the world seems to rotate when we move in it? The expansion of space allows us to theoretically fit any number of squares around a vertex. Computationally, though, there are some limitations due to rounding off errors, large values, or values being too small. This clip contains an example of 8 squares around a vertex. Remember though that we cannot have any other number than 4 when using equal size squares around a vertex. In fact, they don't even need to be squares. They can be any polygons and we can have almost any number of them provided they satisfy some base conditions. Observe 6 pentagons at a vertex. Note that we are going to start at the V-style and cycle through the polygons around its bottom right corner. Also note that the dark green tile is right towards our top. We will note its position again at the end. When we are directly on top of them, we can see their real geometry, but they are distorted when we move away. All of the polygons except the first are obtained through reflection in sides also dictated by the Minkowski distance of measure on the hyperboloid. Also notice that the green pentagon is now towards our left, even though we have returned to the same position. This effect is holonomy, and to understand this we need to understand hyperbolic rotations and player movements through the world. Let us look at a player standing on top of a circle. This circle can actually be thought to be the projection of a hyperbola. If the player wants to move forward, there are two things we could do. We could either translate the player forward, or we could rotate the world back, and it would give the impression that the player has translated forward along the surface of the sphere. We want to accomplish the same on a hyperboloid. Looking back at our example of the hyperbola, we position the player at the tip of the hyperboloid. We already know that the distance between P0 and P1 and P1 and P2 is 1 unit. Thus, if our player were to attempt to move 1 unit forward, he would reverse rotate the world, and the point P1 would map to P0, P2 would map to P1, and P0 would be 1 unit behind the player. The distance between the points given by the Minkowski metric should be preserved. Luckily, we have hyperbolic rotation matrices which accomplish just that. Note that hyperbolic rotation matrices contain hyperbolic functions. Let us see the action of this matrix on the points of a hyperbola. The hyperbolic rotation causes the hyperbola to slide along itself, thus giving the player the impression that he is moving through the world. While moving between squares and polygons in the above shown level, this is how movement was simulated. Once we have understood player movement through the world, we are in a better position to understand holonomy. Holonomy means that as we move through the world, we accumulate extra rotation, and this is best shown than explained. You will notice that in the above video, when we start off, the dark blue region is towards the right, but as we travel around a closed loop and return to the same position, the dark blue region has skewed downwards. The same pattern can be observed in our implementation of hyperbolic space as well. The red tile started off at our right and ended up at our left. From a computation perspective, it is not fixed which tile is to the left or top of a current tile and needs to be computed in real time.
Up till now, we have been simply stating that we are viewing the hyperboloid from the bottom up. To extend to a higher dimension, we will need to formalize this a bit more. To view the hyperboloid on the screen, we take its position like so. The center of projection lies at 0001 or 00-1. The image plane is always 1 unit above the center of projection, and the equations for this are simple and left as an exercise to the reader. Each of the center of projection results in a different model of the hyperboloid. This figure demonstrates the Poincare model. The brown line, which counts as a straight line or geodesic on the green hyperboloid, as it curves along it, is mapped onto the red line, which is also a curve. By contrast, as shown by the figure on the top, the other center of projection results in the Klein model, and the same brown geodesic is now mapped onto an actual straight line. Both of these models can be used to view the hyperboloid in our implementation. While the Poincare model offers us a better view of what's happening in hyperbolic geometry and thus gives us a better understanding of how it works, the Klein model is uncompromising, and because of all of the effects of hyperbolic geometry that we mentioned before, it's much easier to get lost in this mode, and it offers a completely different playing experience. With the aid of this concept of projections, we can extend the effects of hyperbolic geometry to even higher dimensions. Currently, we only had a two-dimensional hyperboloid that satisfied the equation on the left, embedded in 3D space. So we were essentially exploring what a hyperbolic plane would look like. To explore the hyperbolic 3D space, we need to embed it in 4 dimensions. And similar to how we projected onto a unit disk before, now we will project onto a unit sphere. The equation for this is shown on the right. As before in 2D, our character will stay fixed in place and our world will move in response to the character's movement. 4-dimensional space offers 6 rotation matrices about each pair of axes. The right 3 hyperbolic rotations are used to simulate the player's movement, moving forward, sideways, and jumping. The left 3s are standard Euclidean rotation matrices and are used to enable the player to look around the scene using a mouse.
After projecting onto a unit sphere, we position the player at the origin, looking at or along one of the axes. But first, we will look this from the inside to see what rotations do to the points on the sphere. This is the demonstration of the Euclidean rotation. The sphere rotates in response to the player looking at left or look up or tilt his head sideways. The hyperbolic rotations are used to simulate players' movement throughout the world. For example, when player tries to move vertically down, the points move up. Similarly, when the player tries to move vertically up, the points move down. When the player moves horizontally, the points move in opposite direction. Finally, if the player tries to move into or out of the screen, we get this. Finally, let's put all of this together. Remember this 2D level? Now we are going to turn these squares into rooms and place the player inside of it.
All of the discussed effects of hyperbolic geometry still hold. Even though none of the rooms are at a distance of more than 2 units from the starting position, it still seems like we are in a very large space, demonstrating how the hyperbolic space is much larger than the Euclidean one. Let us pose a fun question now. In the following video, which room is directly opposite the current room? The green room or the pink room? The answer is neither, since there are in fact 7 rooms around a vertex or a pillar, and thus there is no room directly opposite the current one.
There's an already existing game called Hyperbolic Sokyukuban, where the aim is to push specific blocks on specific tiles in right direction and orientation in order to solve the puzzle. As we mentioned in a proposal, there are no framework to build hyperbolic games, and thus the developers have to code these games through scratch again and again. Our library API allows levels and player movement to be implemented in less than 150 lines of code. Further objects can be added as the creator seems fit. The level you see on the screen right now was defined and created using the text file on the right, which our API can read. Similarly, we can generate any level through our API provided that the text file follows the same format. Now in the next few slides you will see that how can we import objects into hyperbolic spaces using mesh files, and how the imported object is distorted into hyperbolic geometry.
Along with creating rooms and importing levels, we can also import objects into the hyperbolic space. This is done using their mesh files, which consist of vertices and faces denoting the geometry of an object. After being imported, the object is distorted to the geometry of hyperbolic geometry. This is the mesh of a windmill that can be viewed from different angles. Previously, our windmill looked a bit colorful. That is because the mesh consists of triangles and each triangle had been given a different color to make the shape of the windmill apparent. Here we give the entire windmill a static color of red. Now it is very hard to distinguish between the micro details of the windmill, and thus we turn to the lighting and shading models. Lighting and shading models allow us to see features of the windmill that were not visible before, even when using the color triangles. We can see the stairs as well as the windows. The lighting and shading models involves placing a light source inside the scene so that parts of the windmill which face towards the light source are brighter and other parts that face away are darker. In this case, the light source has been placed towards the bottom of the windmill, which makes the bottom brighter compared to the top. If Currently, we're using cosine shading, which involves calculating the angle between the face normals, that is the normals to the triangles previously shown, and the direction of the light source. Since the calculation of the cross product and the face normals differs in hyperbolic from Euclidean, we had to manually derive it. Another feature of hyperbolic space is that walking around objects takes a much longer time than walking through them. This is because hyperbolic space is much more expansive than Euclidean space. Since we've already been talking about importing meshes and distorting them to the current geometry, it should also be mentioned that the larger a mesh is, the more it distorts, and sometimes it becomes disfigured. So sometimes we squish the meshes to solve this problem. As can be seen here, walking through the windmill took a much shorter time than it took to walk around it. Now we will climb the stairs for added effect. Importing levels and importing objects does not have a this or that relationship. We can have both of them at the same time. Here several windmills have been imported into our hyperbolic level. From the room we currently stand in, we can see the red windmill hiding behind the pillar, and it should be in the room left to the room in front of us. But when we go to it, we find that in fact it takes two additional rooms to reach back to the red windmill, and takes a total of 6 rooms to reach back to the yellow windmill. This is in the same spirit as having a large number of polygons around a vertex. We can have a large number of rooms around a vertex. The hyperbolic space is much more expansive than the Euclidean space, and this is just another example. For the final touch, we apply texturing. Texturing involves applying small repeated patterns to the surface of the object instead of simply applying color. In conjunction with lighting and shading, this gives very realistic results. Here the windmill appears as though it is made out of bricks. Now, with our basic architecture in place, we can now work towards importing entire levels into the hyperbolic space. Here we attempt to simulate an entire forest as a level in hyperbolic space. We have meshes of trees, rocks, and the ground with colors applied, and the lighting and shading models also in place. Features of hyperbolic space may also be spotted, such as distortions in the shape of trees and rocks, even though they were made from exactly the same Euclidean meshes. Another feature of hyperbolic space that may be spotted is that objects tend to grow smaller faster as they fade into the distance compared to their Euclidean counterpart. Finally, we have an intricate level on our hands. This is the interior of a spaceship, the mesh of a spaceship, with both small and large objects and subtle and major details. The distortions caused by hyperbolic geometry, as before, can be observed to the pillars and walls, and we can enjoy the view with a wide angle that is also a feature of hyperbolic geometry. Thus, in conclusion, our project has explored a space that is very different from the Euclidean space that we are familiar with different rules of even the most basic and fundamental mathematical concepts. We have been able to import meshes, create levels, and render entire scenes in real time from the first person's perspective, and our characters are able to explore them freely. Thank you for listening to our presentation. If you have any questions, you may drop them below. This is Future Gadget Lab, the future, signing off.